God, I hate this physics. I don't understand it.
Hello, kid. Do you also hate physics? Well, physics can be fun, but first you need to hop into my super cool van, okay? Get in. Now we're gonna travel across the time and space to find the best physicists on the planet to explain you dumbass, how does the quantum physics work. Are you prepared?
Yeah.
Yeah. What happened just a second ago in my time machine? I said but it's a time machine. It was supposed to be a secret. Let's go meet my great friend here in the higher students. We're gonna find the great physicist Max Planck.
Are you here for the quantum physics lesson? I certainly hope so. Come inside. There's so many villagers. I hate those guys, bro. Get out! Get out! Leave us alone! They're armed and dangerous! There's more of them? Even children? God, I can't stand them. I can't stand them. Get rid of them all! All of them! Die! Okay, so, now we have a full place to ourselves. Let me get started.
Have you ever stopped to wonder what light actually is? Or how energy truly flows through the universe? I have. And that question led me somewhere unexpected. At the end of 19th century, physics felt nearly complete. Newton had described how objects move. Maxwell had revealed the secrets of electricity and magnetism. To many, it seemed as though we had figured it all out. But I had a problem. A very specific, stubborn problem. Blackbody radiation. A blackbody is a perfect absorber and emitter of radiation. When heated, it glows red, then orange, then white, and blue. The color depends on temperature, but when physicists tried to describe this behavior using classical physics, the math just broke down. As the frequency increased, the predicted energy output shot toward infinity. That would mean something warm should emit endless energy in the ultraviolet range. Clearly, that was wrong. We called it the ultraviolet catastrophe. No matter how we twisted the equations, the problem remained. So in the year 1900, I did something radical. Not because I wanted to start a revolution, I just wanted to fix a math problem. I asked, what if energy isn't continuous? What if it comes in tiny discrete packets, like chunks? Imagine a staircase. You can't stand between steps. You're either on one step or the next. I proposed that energy works the same way at microscopic level. It doesn't flow smoothly, but jumps from one level to another. And these chunks of energy I called quanta. To describe it, I used a simple equation. E equals h times v, where E is the energy of a quantum, v is the frequency of radiation, and h is a constant I introduced, now called Planck's constant. It's a very small number, but this small number changed very big things. In 1905, Albert Einstein took my hypothesis a step further. He applied it to light itself, proposing that light was made of individual particles, photons, each carrying a quantum of energy. That bold idea explained the photoelectric effect, why light could knock electrons off a metal only if its frequency was high enough. It wasn't about intensity, it was about frequency, just as my equation had said. Einstein won a Nobel Prize for that, and it proved something I hadn't yet dared to believe. Energy is quantized. and so is light. My original goal was modest, fix a math problem. But that one idea opened the door to a new world, the world of quantum physics. In 1918, I was awarded the Nobel Prize in Physics for this work, and today my constant, h, is one of the most important numbers in all of science. In fact, since 2019, it was even used to define the kilogram itself. So, the next time you see a beam of light or hear the word quantum, remember, it all started with a simple idea, that energy doesn't flow smoothly, but in tiny, indivisible pieces. Sometimes the biggest breakthroughs come from the smallest steps.
So you understood everything that I taught you, right? Well, that's really good. Well, I'll be heading home now. What happened? Oh no, what? There's a shootout out there? Quick, get in! Get out, little Billy! We don't need you right now! Die! Quick, go, 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 go! Drive, 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 drive! Oh, thank God that was close. I really hope my friends are okay, you know? Oh, me? Well, I am Niels Bohr. And no, I wasn't looking at little Billy. What? That would be disgusting. I was looking at his atoms, right? Atoms. Those tiny little things, right? Have you ever actually wondered what atoms really look like? Not just as those tiny invisible dots, but how they're structured? Where are the electrons? Why atoms behave the way they do? Well, these questions fascinated me, and in 1913 I set out to find an answer. We already knew atoms had a dense, positively charged nucleus, thanks to Ernest Rutherford's famous gold foil experiment. He showed that most of an atom is empty space, with a tiny, tiny heavy center that could deflect fast-moving alpha particles. But there was a serious problem with Rutherford's model. According to classical physics, an electron orbiting the nucleus should be constantly accelerating. That means it should emit radiation, lose energy, and spiral into the nucleus in a split second. That clearly wasn't happening. Atoms were stable. Something was missing from our understanding. That's when I had an idea. A strange one, drawn from the new world of quantum theory. What if electrons don't orbit the nucleus at just any distance? What if they're only allowed in specific orbits? Quantized energy levels, like steps on a staircase. Each orbit would have a specific amount of energy. Electrons wouldn't radiate energy while staying in one orbit. They'd only emit or absorb energy when jumping between levels, by releasing or absorbing a photon with an exact energy difference. And mathematically, I found a formula that worked, where r is the radius of the orbit, n is a whole number, h is Planck's constant, m is the electron mass, k is Coulomb constant, E is electron's charge. This meant that atomic radius is quantized too. Electrons can't just float around randomly, they're locked onto fixed tracks. The first orbit is the smallest and closest to the nucleus. For hydrogen, that radius is very small. We now call it the Bohr radius. And then something wonderful happened. My model explained the hydrogen spectrum, those strange specific lines of color you see when excited hydrogen gas glows. Electrons in hydrogen don't release just any energy. They jump between quantized orbits. Each drop from a higher orbit to a lower one releases a photon with a precise amount of energy and a specific color. The math worked. The predictions matched the observed lines perfectly. For the first time, we had a model that connected quantum theory with atomic structure. My model wasn't perfect. It worked beautifully for hydrogen, but not for more complex atoms. The orbits got messy. Reality, as it turns out,
is more wave-like than we imagined. But the core idea that electrons exist in quantized energy levels endured. It became a cornerstone of modern quantum mechanics. In 1922, I was honored with the Nobel Prize in Physics. But more than the award, it was the realization that nature at the atomic level doesn't follow the smooth, continuous rules of classical physics. Instead, it dances to the rhythm of quanta. So the next time you see a neon sign or look up at the stars, remember that light comes from electrons falling between steps in the quantum world. And it all started with a simple idea that atoms, like music, move in discrete notes, not a continuous hum.
Oh, sorry, I got carried away. Where are we? No, 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 not the FBI. I'm not doing this again. No, I am not. No, I am not. No, 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 I'm running away. You can't catch me. You don't know anything. Uh-oh.
Hello. Einstein is dead. My name is Albert Einstein. I was born on March 14th, 1879 in Ulm, Germany. And what I am about to say may sound unbelievable, but every word of it is true. For most of history, we thought we understood gravity. Newton said it was a force, one object pulling on another. Made sense. It worked. It sent rockets to the moon. But it wasn't the truth, not the full truth. In 1915, I introduced something that changed everything. A theory that didn't just rewrite physics, it rewrote reality. I called it the general theory of relativity. It says gravity isn't a force. It's not some invisible hand pulling you down. It's the warping of space and time, the fabric of the universe by math and energy. You're not being pulled, you're falling along curves in space-time you can't see. Mass bends space, energy twists time. The universe becomes a stage where matter and geometry perform a quiet, endless dance. I captured it all in one set of equations. Just one line, 10 equations, really. On one side, how spacetime curves. On the other, what causes the curve? Mass, energy, pressure. It means that stars, planets, even light itself follow the bends in spacetime. It means black holes aren't fiction. It means time itself runs slower near massive objects. In 1919, during a solar eclipse, we tested it. Light from distant stars bent as it passed the sun, exactly as I predicted. That day, the world believed in me. That day, the old universe died. And this one, new one, twisted, curved, impossible, was born. You probably use it every day. Without corrections from general relativity, satellites would drift, your map would lie, planes would be lost. And yet, even now, it still unsettles me. Because I didn't just uncover a new way of seeing gravity, I uncovered a truth so deep, so strange. It makes the universe feel less like a machine and more like a story written in invisible ink. I didn't set out to change the world, I just followed the math. But once you see the curvature of space, you can't unsee it.
What? Okay, ignore all of that. I'm Schrodinger, and we're gonna tell you what I did later on. But now, this. I can't stand him.
This is Heisenberg. In 1925, Heisenberg, only 23 years old at the time, proposed a bold idea. Forget about trying to visualize the exact path of electrons. Instead, focus only on what we can actually observe. Things like the frequencies and intensities of light emitted by atoms. Heisenberg realized that trying to imagine an electron's precise orbit around a nucleus was pointless. In the quantum world, certainty about position and momentum was impossible. To capture this new way of thinking, Heisenberg developed matrix mechanics. In this formulation, physical properties such as position and momentum are not simple numbers. They are matrices, grades of numbers that interact according to specific mathematical rules. An important feature of these matrices was that the order in which you multiplied them mattered. In math, we call this non-commutativity. In classical mechanics, multiplication usually commutes, but in Heisenberg's quantum world, position and momentum matrices did not commute. This led to one of the most famous ideas in physics, the Heisenberg uncertainty principle. In plain language, the more precisely you know where something is, the less precisely you can know how fast it's moving, and vice versa. This is where things get a little less intuitive, and it's deeply connected to the idea that at the quantum level, particles don't just behave like tiny balls, they also behave like waves. Imagine a wave on the surface of water. If you want to know the exact position of the wave, you might try to pinpoint a single peak, but a single peak doesn't tell you much about the wave's overall speed or direction. On the other hand, if you want to know the wave's momentum accurately, you'd look at its wavelength and how fast the pattern is moving. But to do that, you need to observe a larger part of the wave, which means you're less certain about the precise location of any single point on the wave. Particles in the quantum world are similar. They don't have a single definitive position and a single definitive momentum in the same way a baseball does. Their nature is spread out like a wave. In Heisenberg's view, the world at the quantum level is not a place of neat trajectories and predictable motions. Instead, it's a realm of probabilities and limitations.
I've had enough of this. I will teach you real quantum physics. Follow me. While young Heisenberg was busy constructing his matrix mechanics, an abstract but ingenious framework, I was approaching the quantum riddle from a very different perspective, one that resonated more closely with the continuity of classical physics. You see, I had long been captivated by the strange notion of wave-particle duality. The experimental evidence, such as photoelectric effect, made it clear that particles, electrons for example, were not merely point-like entities, but could also exhibit wave-like behavior. This idea stirred something in me. I began to ask, what if electrons were not tiny, discrete balls zipping around the nucleus in fixed orbits, but instead were described by waves? Waves that extend in space, evolving smoothly, like ripples on a pond. In 1926, I introduced what has since become known as the Schrödinger equation, a differential equation that governs the behavior of these quantum waves. The trident is the wave function, H is the Hamiltonian operator representing energy, and E is just the energy. The wave function, the trident, contains all the information about the quantum system, including information about its position, momentum, energy, and the rest of the properties. This conception was revolutionary. Particles, I realized, do not possess definite positions of momenta until they are observed. Instead, they exist as superposition, a cloud of probabilities, each outcome with its own amplitude. This was not mere mathematical abstractions.
It was a radically new image of reality. At first glance, my wave mechanics and Heisenberg's matrix mechanics seemed irreconcilable, two competing theories, but soon it was shown that they were mathematically equivalent, merely two languages describing the same strange quantum world. His method emphasized discrete transitions and observable quantities. Mine, the smooth evolution of the wave function. Together, our approaches laid the cornerstone of quantum mechanics, a theory capable of explaining the inner workings of atoms, the glow of semiconductors, the function of lasers, and the dynamics of stars and black holes. In 1927, we stood shoulder to shoulder at the Solovey Conference, in the company of giants Bohr, Einstein, and others, as we debated not only how quantum mechanics functioned, but what it meant. Look at this paradox. One has lava, the second one nothing. Do you dare to pull the lever? Oh no. Oh, you thought mere bullets could kill me? I am Einstein. I am undefeatable, and I will destroy you with the power of quantum physics, unless you can prove me wrong. We have to stop Einstein. By the 1930s, I had watched quantum mechanics grow into an incredibly successful theory. It explained the structure of atoms, the nature of chemical bonds, and the strange behavior of subatomic particles with impressive precision. And yet, despite its success, I couldn't bring myself to fully accept it. I admired its power, of course, any honest scientist would, but certain implications deeply unsettled me. The idea that nature was fundamentally random felt wrong, and the notion that simply observing something could determine its reality, that ran counter to everything I believed about the physical world. I said it plainly and often. God does not play dice with the universe. To me, quantum mechanics was incomplete. I was convinced there had to be a deeper layer of reality beneath the apparent randomness, one governed by precise deterministic laws. In 1935, I joined forces with two brilliant colleagues, Boris Podolsky and Nathan Rosen. We decided it was time to bring our concerns to light. Together, we published a paper titled, "Can Quantum Mechanical Decryption of Physical Reality be Considered Complete?" Today, people refer to it as the EPR paradox. We started from a simple but powerful principle. A complete physical theory must describe every element of reality. But what exactly qualifies as an element of reality? In our view, it was straightforward. If you can predict the value of a physical property with certainty without disturbing the system, then that property must correspond to something real. In other words, if you can know something about a system without touching it, that something must exist as definite, real feature, not just a probability. Seemed reasonable enough. Then we turned to quantum mechanics and showed that it fails this test. We proposed a thought experiment. Imagine two particles that interact, then fly apart in opposite directions. Because of their interaction, their properties, position, momentum, become entangled. According to the rules of quantum mechanics, you can know both the exact position and exact momentum of a particle at the same time. That's Heisenberg's uncertainty principle. But here's the strange part. If you measure the position of one particle, you instantly know the position of the other.
even if it's light years away. And if you measure its momentum instead, you know the other's momentum. This meant that you could choose what to learn about the second particle simply by deciding what to measure on the first, without even touching it. To us, that pointed two deeply troubling possibilities. 1. Information might be traveling faster than the speed of light, a clear violation of my own theory of special relativity. Or, the particles must have been predetermined properties, so-called hidden variables, that quantum mechanics doesn't account for. We favored the second option. We concluded that quantum mechanics, powerful though it was, didn't tell the whole story. A deeper theory, one including hidden variables, was needed to describe physical reality completely. Our paper sparked a strong response, especially from Niels Bohr and his supporters, who upheld the Copenhagen interpretation. Bohr argued that we had misunderstood the nature of quantum measurements. In his view, quantum properties don't exist in a definite state before measurement, not because of ignorance, but because they simply aren't real until observed. He insisted that the system and the act of measuring it were inseparable, that quantum reality itself is shaped by observation. So while our thought experiment did reveal a real paradox, Bohr believed it didn't call for hidden variables. Instead, it highlighted the fundamentally strange and interconnected nature of the quantum world. For years, our challenge to quantum mechanics was treated more as a philosophical issue than a scientific one. Most physicists kept using quantum theory as a tool, setting aside the deeper questions. But I knew we had planted a seed. We had raised a profound question. Could the universe really allow for such deep non-local connections, what I called spooky action at distance? Was it just an odd feature of the math? Or was it something?